Alrighty, so fundamental unit charge, the Millikan experiment. There he is there, Robert Millikan. Most electric charges are measured in coulombs. In the famous experiment known as the Millikan experiment, Robert Millikan discovered the charge on one single tiny electron. That was the point of the whole thing. This charge is known as the elementary charge. Elementary or fundamental. It's the smallest possible charge there is. Abbreviated to 1 ELCH. EL elementary CH charge. And he found one electron to have a charge of 1.6 times 10 to the minus 19 coulombs. Now, he didn't find that number. Megan, I know you know the number. Or you found it. Do you remember? 1.5.
No.
5 something, right? Okay, so he got a little bit off, which is understandable. This is well over 100 years ago. The common everyday number, I think, is 1.602 now, right? Probably found that. So we're just going to use, just for simplicity's sake, the number we're going to use is 1.6 times 10 to the minus 19. And I've shown you how to do that scientific notation on your calculator. Was there anyone that was away that missed that scientific notation? There was a couple people that were away for it. Okay, so we might have to do that with your calculator. Okay, so he found that when tiny oil droplets were subjected to X-rays, they become ionized and thus charged. So he fired an X-ray at them. And when I say ionized, from chemistry, what does that mean? You have an ion. They lose or gain electrons, that's right, and they have a charge, positive or negative. If they lose electrons, they have a positive charge. And if they gain electrons, they have a negative charge, right? If they have excess electrons, extra electrons, they become negative. Some would have charges of -1, -2, or -3. They thought that if you measured the total charge on a droplet, it would be a small multiple of that fundamental or elementary charge. So he was in fact looking for the multiples of that elementary charge. This apparatus looks like this. You probably saw a picture like that when you were researching, right? Okay, so now many places, some descriptions of the event say that he used X-rays. Some descriptions say that just because he was spraying the oil into the container, that friction was charging them. I'm guessing X-rays were probably used. So he sprayed this fine little mist into the top container here, and some of those oil droplets fell down through this hole. And he had a charge plate on top, and he had a charge plate on the bottom. They were hooked up to a battery. This is the symbol for battery that you probably learned in grade 9. And he had a microscope over here. And he watched for oil droplets. They would be falling, some would be rising, and some would actually do what? Be suspended. Okay? And it all depended on what the charge was on that particular oil droplet. And you could observe it with his microscope. The handles are right here. Top plate is positive and the bottom plate is negative. You might want to just, I don't know, do you have that on your little handout there? You might want to just make that little note there. So that would make, for these oil droplets here, maybe I'll just draw it like this. I'll draw it big like this. Obviously not to scale. So for that to be attracted to the top plate, what charge would it have to have? It would have to be negative as well, right? So that charge on the oil droplet is negative. It's attracted to that top plate, the positive, and the bottom negative plate is pushing away. The electric field from positive to negative, right? The electric field is actually this way. But remember, that's the direction that what kind of charge would go? A positive one, right? So the negative one goes opposite. So that's what it says here. Millikan sprayed oil onto the top of the plate. Some of the oil fell through the hole. When the two droplets were inside the two plates, they experienced two forces, gravity and the electric field force. So gravity is pulling it down. The electric field force is pushing it up. The force due to gravity could be calculated with Fw equals mg. He knew gravity. When the droplets are sprayed, they receive the negative charge through the plastic nozzle. Sort of not true. He used X-rays. When inside the two plates, they experience an upward repulsive force, and this force depends upon the strength of the electric field because of E equals F over Q. He could adjust this electric field strength to balance he would pick an oil droplet that he liked, and he would adjust the electric field strength until he got it suspended in air. And he could figure out what the weight force was, and that would have to be equivalent to the electric force. So knowing the electric force and the electric field and electric force, he could then solve for Q, which is what he was trying to do. You guys know all this already, right? And there it is there. He noticed that the drops were slowing down, stopped, and moving up depending on the strength of the electric field, which he could control. And these behaviors seem to depend upon mass of the oil droplet. Bigger ones would fall more, obviously. Charge on the oil, the electric field strength. Is there one more? No, there isn't. He knew the density of oil. I'm kind of fibbing a little bit here. This is the way we're going to interpret it. He knew the density of oil and could measure the diameter of the drop through his microscope. A little bit of a fib there as well. He used this to determine their mass and then their weight in newtons. So Millikan's sort of procedure, his steps to arrive at that Q value are a little bit more complex than we want to go into. So I'm sort of going to simulate it with a couple of steps along the way that you guys can easily handle. Okay, so I'm sort of fibbing there a little bit, just to realize that. Since he could adjust the electric field and cause their behavior to change, E was a measure of the charge on the drops. The greater the E, the greater the charge on the drops. And using this information, he calculated the drops' charges and found charge was never less than a certain value. It was always above this magic elementary charge. And number two, all of the charges were a multiple of this minimum charge. Now, I often find that kids really don't understand what I'm talking about there. So I'm going to sort of work it backwards. He knew that he came up with the charge was 1.6 times 10 to the minus 19. But he also found that the charges on some of the drops were 3.2 times 10 to the minus 19. Keep in mind, I'm simplifying things a little bit here. Also, 4.8 times 10 to the minus 19, or 6.4 times 10 to the minus 19. Okay? So these were charges of minus 1, minus 2, minus 3, minus 4 elementary charges. He quite likely graphed all the charges that he found, drew a line of best fit, found the slope, and that was his value, just like we did in the gravity lab. Would he have gotten nice, beautiful, perfect numbers like that? No, of course not. Okay? So again, I'm simplifying things quite a bit. So he found that the charge was never less than this 1.6 times 10 to the minus 19, and that all of the charges were multiples of that. So when the charge was 3.2, it meant that it had 2 extra electrons. When it was 4.8, it meant that it had 3 extra electrons, and so on. It would never really have more than 4. Atoms tend not to gain more than 4 electrons. He concluded that the minimum charge was 1.602 times 10 to the minus 19. Put a star beside that. Should that be on your cheat sheet? Yeah. You will fail miserably this test if you do not know that number. It's a lot of pressure on that one number. Just write it down and get it right. 1.602 times 10 to the minus 19. Is that the last slide? Looks like there's one more. Note that this means that a proton has a charge of, where is it? Plus 1.602 times 10 to the minus 19. Now, I just happen to have a school millikan apparatus, so I'm just going to sort of pull over here for a second. So when we did classroom renovations about, it's probably almost 15 years ago now, I discovered in the back room about 12 boxes of these, still sealed, never been opened. So Mr. Paul, who used to teach out of this room, used to be the mayor of Dauphin, and was a pretty smart guy. We decided we'd try to get one going one day. And we spent a couple hours trying to get it going, and we couldn't get it going. So the way it works is there was a little container right here. They didn't use oil, they used these little graphite, little tiny plastic beads. This was the atomizer here. This one's been sitting around for a while, and I think kids have been playing with it, yeah. There used to be a little rubber kind of ball kind of thing, a little bulb that you would squeeze, and it would shoot the little plastic beads into here. Okay? This is just a light, like a flashlight kind of thing. And if you look carefully from the front here, and you guys will be able to see it, but you can have a look later. You'll see there's two sort of black sort of metal plates that are about a centimeter apart. And then there was a little microscope here that someone's decided to snap off. So it went like sort of like this, and you would measure the fall. And there's a little knob over here that would adjust the electric field strength. You would hook it up to a power source, and you could actually conduct a millikan experiment here at school. Well, apparently, like I said, never been done because there was 12 boxes, never been opened. So we tossed away 11, and I kept one just for demonstration. So you're more than welcome to come and have a peek at that later. I'll send around the microscope. It's kind of cool. It's really tiny. It's got these little markings on it that you could use to sort of, that's the end there. You could use to see the mark how fast they were falling. Okay, so do you have this on that page? Is it answered there? I don't know if it is. Well, it is answered. Okay. Well, this is something you need to be able to do. Okay, so watch carefully here. You need to be able to convert from elementary charges to coulombs. So if the question is, if 1 ounce has 1.602 times 10 to the minus 19 coulombs, how many electrons are required to have 1 coulomb of charge? How big of a box of electrons do you need to get 1 coulomb of charge? Now, about grade 7 or 8, you learned how to do ratio and proportion. I think so anyway, most of that age. There's very little, and I don't feel bad about saying this, there's very little in math that you're actually going to use in real life. You probably know that. This is one of them. Okay, and it's not just for science class. You will use ratio and proportion all the time. So, if 1 elementary charge is 1.602 times 10 to the minus 19 coulombs, how many elementary charges is 1 coulomb? So we're going to cross multiply there. We're going to get 1.602 times 10 to the minus 19. We're going to multiply by x. We're going to take 1 times 1, and you end up dividing by 1.602, and you get this other magic number right there. That's the inverse of the millikan number. 6.25 times 10 to the 18 elementary charges. 625 with 16 zeros. 625 with 16 zeros is how many elementary charges you need for 1 coulomb of charge. And we'll do some conversions a little bit later. Okay? I don't know how well you can see. You guys kind of look at the light. Yeah. Look into the light, Brandon. Yeah, not the sun though. Don't look into the sun. Okay. So there you go. Do you have these questions as well in your little package there? Yes, you do. Okay. So that was real exciting, but here comes the actual math part. So you'll need to write these down. I'm going to go get my notes so that I don't screw this up. Okay. So I want to caution you, some of you that still haven't realized, when I do sample questions, you're going to do problems just like this a little bit later. So here's 3 in increasing order of difficulty. Again, really crazy, weird numbers. Small ball of mass 6.5 times 10 to the minus 6 kilograms and charge of 1.5 times 10 to the minus 10 coulombs is suspended in air above an electrically charged plate. Look for that word. Oh, that was supposed to be a highlighter. Look for that word suspended. It means something special. It means that the forces are balanced or equal. It's like constant velocity in the other ones. In the air above an electrically charged plate, what field strength is required to suspend this particle in the air? So let's just look at what we do have and what we're trying to find here. We know the mass. 6.5 times 10 to the minus 6. We know the charge, which is the letter Q. 1.5 times 10 to the minus 10. And we are solving for what field strength? We are solving for E. Okay. I always draw a little picture just to help kids visualize things. The weight force, gravity down, is balanced by the electric force up. Okay? And we're trying to find E, which is in this formula here. So we're going to have to get FW first. How do you find FW? It's equal to mg. The mass is 6.5 times 10 to the minus 6 times minus 9.8. 6.37 times 10 to the minus 5 newtons. Negative, implying down. Which means what? What's the next step? I'll give you a hint. Yeah. That means, therefore, the electric force is plus 6.37 times 10 to the minus 5. I guess I could write that out and show the net force is 0, but I think everyone can do that. These forces are equal. One is negative and one is positive. One is down and one is up. Bailey.
I'm getting negative 6.37 times 10 to the minus 15, not negative.
Oh. Did you go 6.5 times 10 to the minus 6?
Yeah.
You must not have. There's no way. Okay, so what field strength? So now I'm going to solve for E. E equals Fe over Q. 6.37 times 10 to the minus 5. Charge is 1.5 times 10 to the minus 10. Okay, so here's the double scientific notation. So I'm just going to pause there and I'm going to let you pull out your calculator and try to get the answer because you need the practice on it. And I'm going to go do my attendance. You should get 424,667 newtons per coulomb, or 4.2 times 10 to the 1, 2, 3, 4, 5. 4.2 times 10 to the 5 newtons per coulomb. Either one is fine, Megan, yes, absolutely. Ten to the 0. I know why. Because I messed up. I sure did. 1.5 times 10 to the minus 10, and I wrote so that number that you got, when those exponents are the same, do you guys know about exponent laws? I know you do. I know this is in grade 11 pre-calc. When they have the same exponent, they cancel, right? You do that subtraction thing when you divide, right? So minus 5 subtract minus 10 is going to give you plus 5, right? So there's your little check to see if you did it right. That's how I knew what I'd done wrong. Because when he said times 10 to the 0, I looked here at my exponents and I realized, oh yeah, that's not supposed to be. Okay? So 4.2 times 10 to the 5. Now, let's say you had made that mistake on a test. That question's worth 2 marks. What should I do? Not 1.5? Renee thinks 2? Just mark that, so it's like 2 out of 2. You know what? If you caught me on a particularly good day, and you've demonstrated that you have a pretty good understanding of all this, and all you've done is just sort of make a little boo-boo, and you typed it in, right? You don't have to use your calculator. What you can't do is apparently read. On a particularly good day, you might get 2 out of 2. Yeah, Dan, I might do that. But that's the beauty of showing your work, because if you don't show your work, and just get that answer, I'm going to go, well, I don't know how they got it. They must have copied off someone, and that other person got it wrong. So tough luck for them, I guess. So show your work. Okay, are we ready for example 2? I'm pointing out these are getting increasingly more difficult. Pay attention. I'm going to make a small change to the question. I'm just going to go in Elches. That's all I'm going to do. Relax. In Elches. Okay, so now we've got a small sphere, mass 7.0 times 10 to the minus 8, suspended in midair above a charged plate. At the point in the air, the electric field is 300. What charge is on the sphere in Elches? So this time we're solving for the charge, and this time we need our charge in elementary charges. So the mass, see it says mass. Mass is 7.0 times 10 to the minus 8. The electric field is 300. E is 300 newtons per coulomb. We are solving for charge. We don't know the charge. Again, weight force is balanced by electric force. So let's find our weight force. So our weight force is negative 6.86 times 10 to the minus 7. Therefore, the electric force is plus 6.86 times 10 to the minus 7. How come we don't change the sign on the exponent? Should we be doing that? Should we be changing that to a plus 7? No, don't do that. It's the sign out front. That minus 7 just means this is 0.000000686. If you put a plus 7, then it's 686,000. It's like 686 million. Right? Negative exponents mean small numbers less than 1. Positive exponents mean big numbers much bigger than 1. Okay, so that's my FE. E equals F over Q. The electric field strength is 300. My E value is my FE is 6.86 times 10 to the minus 7. You're solving for Q. Now, we've had this situation many, many times. Involuntary math. You have to be able to solve that without even blinking. You need to know how to do that. I hope you do. You switch them, right? These two just switch. 6.86 times 10 to the minus 7, all over 300. Is this exponent going to get smaller? You've got a small number and you're dividing it by 300. It's going to get even smaller, isn't it, right? And you should be able to, I can tell you right now what exponent that's going to be, because I'm dividing by minus 2 here, or sorry, 2 decimal places, so that's going to become minus 9. You're going to get 2.29 times 10 to the minus 9, and that's in coulombs. Everybody with me so far? I realize it's not even close to anything. How do I convert it now to elementary charges? That's that whole ratio thing you learned in grade 7. Who'd you have for grade 7 math? Did he teach you that? You weren't listening, right? Probably talking baseball. Yeah. No? Hockey. Canadians. Yeah. Just like. I taught him too. I didn't teach him not to cheer for the Canadians. Okay, so we're going to write 1 elementary charge is 1.6 times 10 to the minus 19 coulombs. So we're solving for x over 2.29 times 10 to the minus 9. And then how do you solve those ratios, those proportions? Cross multiply. 1.6 times 10 to the minus 19x. That one times that one. 1 times 2.29 times 10 to the minus 9 is going to give me another 2.29 times 10 to the minus 9. Yes, I know it's crazy. You got to write these numbers out over and over again. When you think how much time you've wasted there, think about how many times I've had to do it. Problem, Hannah? You sure? You've got the I don't get this oppose. Alex? 2.29 times 10 to the minus 9, this number here. I'm taking this number here, and I'm converting to, yeah. So what am I going to do here? I'm going to divide both sides by 1.6, right? So x is equal to 2.29 times 10 to the minus 9 all over 1.6 times 10 to the minus 19. I'll pause for a second. Okay. So, many students say to me at this point, can't we just take that number and divide by 1.6 times 10 to the minus 19? And the answer is yes, by all means. But don't you dare ask me, do I multiply or do I divide on the test? Because sometimes you're going to have to divide by this. When you're going from coulombs to elementary charges, you divide. But when we're going from elementary charges to coulombs, you have to multiply. Just like multiplying by 3.6 and dividing by 3.6. I am not answering that question on the test. Do I multiply or do I divide? The only way to guarantee it is to do it like this. You do that cross multiply, it'll all work out beautifully. Even me, years of experience, I still do it this way because I can't remember. I still do it this way. Dan.
So if we're doing out a test, we have whatever that pretty much, like
Yeah.
just multiply or just divide by whatever.
You go right ahead.
Can you just write coulombs equals this?
Yeah.
You have to write whatever. You can also write whatever else.
Elches, elementary charges. Yeah.
Whatever
Yeah.
times.
You do what you need to do, but I am not answering the question, do I multiply or divide on the test? I'm going to say use your ratio, because it's a beautiful use of that. Okay, so my answer ends up being a really large number, 1.43 times 10 to the 10, and that is elementary charges or Elches. This plastic sphere has a charge of 1.43 14 billion electrons. Okay? So what's different in this question, Brendan, from the previous one? Here I found the weight force, the electric field strength. Here I use the weight force, I use the electric field strength to find the charge, and then I convert it to coulombs. I got one more for you, one even harder. That's only 3 steps. Oh, crazy talk, right? I know. Don't worry, Shelby, I'll explain. Okay, this is as hard as they get for the suspended ones. Okay, again, you might remember me saying a little while ago, I said that millikan steps to get there were fairly challenging. I'm not going to make you do them all. I'm going to sort of simulate that with a couple of steps that I believe that the average grade 11 student can handle. So what I'm going to do is I'm going to give you the radius of the oil droplet. I'm going to pretend that he had a little tiny ruler and he can measure the radius. And he knows the density is always 800. There's another number that needs to be on your cheat sheet. I always get one kid a year that says, I don't remember what the density of oil is. And I'll say, is it on your cheat sheet? I don't know. Put the 800 on there. So I'm going to give you 4 steps. It's going to take a lot of space. You can do it. Determine the charge of the droplet in coulombs. So we have the radius here. Did you notice that it's in centimeters? Do you have a funny feeling it should be in meters? See how this says 800 kilograms per meter? Meter cubed? So yes, it's got to be in meters. So your step, say again? It's going to be even smaller. 2 more zeros. How do you convert centimeters to meters? Divide by 100. Add 2 more zeros. So the radius is going to be 0.0006 divided by 100, or 6 times 10 to the minus 6 meters. If you don't do that step, that's just 1 out of 5. 4 out of 5 is your total. You got to do that step. Sometimes I'm a jerk, and I don't give you the radius, I give you the diameter. What should you do? Divide by 2. Who can divide by 2 out there? Just about everybody. Who can tell the difference between the word radius and diameter? Again, just about everybody. Just got to be careful. So 6 times 10 to the minus 6 meters. I took the radius and divided by 100. Everybody with me so far? Good? Okay. Here's a crazy question. Anyone know the volume of a sphere? The formula? It starts with V. Volume equals. It does have pi in there. Oh, you're close. 4/3 pi r cubed. 4/3 pi r cubed is the volume of a circular sphere, a ball. 4/3 pi r cubed. I'm just going to give that to you. I'm not going to tell you where it comes from. It comes from the math store. They're on sale this week. 2-for-1 formulas. I'm going to give you 2 today. 4/3 pi r. So the r is 6 times 10 to the minus 6, and that's going to be cubed. Some of you will have an x to the 3 button on your calculator. Some of you will have an x to the y button on your calculator. You're going to use it. You should have a pi button on your calculator as well. Use it. Okay, go ahead, get your calculator out and give it a whirl. 4 divided by 3 times pi times 6 times 10 to the minus 6 cubed equals. I lost you at pi, Josh? I like Saskatoon pi. Sometimes it's hidden under a second function. Go ahead and try it. Are you going to get a tiny number? Yeah, the volume of this sphere is going to be incredibly tiny. You should get 9.05 times 10 to the minus 16 cubic meters. 9.05 times 10 to the minus 16 cubic meters. Okay, the next step is we have to take that volume and we have to convert it to mass. Here's the formula that they used to teach and they don't anymore. So here's that 2-for-1 sale at the math store. D equals M over V. Anybody want to guess? Density equals mass over volume. We did it way back at the start. It's like the circle of life, the circle of physics, back to the very first couple days. What is the density of this oil? It is and shall ever be 800. We are solving for mass, and the D equals M over V. We're solving for mass. I don't know why I use a capital M there. So this volume here goes over here. 9.05 times 10 to the minus 16. The neatest thing about these questions when I'm marking them is that I can always, if you make a mistake, the way it works, the calculator, I never have to like retype a number in. Because this number right now, I'm going to multiply by 800. I never have to retype it in. I can go through your problem in no time because it's all one big giant step for me. As long as you show me your work, I'll know the steps that you did and I can confirm it. So I'm going to take those two numbers and I'm going to multiply them together, right? and I'm going to get a mass. I'm going to take this number times 800, and I can usually tell by the exponents what you've done wrong. 7.24 times 10 to the minus 13 kilograms. Am I going to get all bent out of shape about rounding? Not even close. What's most important here is showing your work in an organized fashion. If I can see the path that you took, you're going to get pretty good mark. If I can, if it's all over the place, not going to happen. 7.24 times 10 to the minus 13. Okay, so now I'm back to where I was in that first question, because now I've converted it to kilograms, right? So what's the next step? What was the first step on the first two questions? Find the weight force. Mass times gravity. Again, we're going to just multiply this number here. 7.24 times 10 to the minus 13. And we're going to multiply by minus 9.8. And we get 709 times 10 to the minus 12 newtons. I didn't hear what you said. Oh, yeah. I thought you said snake bit, and I'm like, what? I thought it was code or something. Therefore, the electric field force is positive 709 times 10 to the minus 12. And now, last step, E equals F over Q. We're solving for charge. E was 0.3. Solving for Q by dividing. Again, I don't have to press clear. I just keep using that number in my calculator. Divide by 0.3 and you get 2.36 times 10 to the minus 11 coulombs. 2.36 times 10 to the minus 11. Were we supposed to express our answer in coulombs? The question does say yes. If the question says it's got to be in Elches, what do? Do the ratio, or for those of you that are lazy out there, 1.6 times 10 to the minus 19, just divide. I don't actually have that number. .48 times 10 to the 8 Elches. If you have to do all those steps, it'd be 6 marks. I won't disagree with you, Alex, on that. What can I make it? What would I have to make it worth to make it worth all that work? Sorry, guys. Okay, so there's a lot of steps there. I understand. Okay, so I've given you 3 sample questions. You've got 15 minutes. I was such a nice guy that I've given you problems here. I gave you answers. I gave you a link and a QR code solutions, and I ran off the solutions for you. So there is no excuse for not knowing how to do them. You can get that. Okay. Oh. Well, it was more the way you said it. Yeah. Was it you? Okay. Oh yeah. Okay. So you need that. And we'll need it. Can I make this come back? Yeah. Divide by 1.6. So what else did you divide? You always I will, so we'll come back to times 10 to the minus 10. No, I would expect so. I would expect so. Okay, I mean, maybe on there. I think I get tired of kids asking me. Oh, yeah. You guys need more light over here, spectators? Very good. If you're having trouble getting started, I suggest just copying the answers out. Seriously. You got the answers, but the detailed solutions, I suggest just talking about. Okay, what's going on here, boys? Should I use this to see your chances of passing this test? If you don't get in? Oh. Oh yes. Yes, thank you for reminding me of it. Thank you for reminding me. So this data is really weird. You know, this is well, first of all, I thought I had the worst handwriting in town, but that's not a compliment. Okay, so how did you guys get this average velocity right here? That's 0.4, right? 0.4? Okay, so the distance, you remember what the distance you used was? I don't know. Centimeters. 0.5. Well, I'll tell you, you took your distance and you went up. No, that's the point. So you took the distance of 0.5, divided by your time, no, 8.57, divided by time, and I get 0.058.
Oh my god.
Oh,
Still gonna get the question wrong.
okay, and then I know the final velocity is give me that. Right?
How much longer is it studying, doing some projects, working on it, and everything else? Yeah, and working.
So what I did was I went question mark, don't know, but I thought, well, they should be able to do this. So I marked this position. Okay? And I didn't even look at this and I thought, well, there's a good chance.
And it didn't post it to
Yeah. Yeah. So that's what I want you to do. No, I just want you to deal with it. You've got the data. Right? But I don't know know how to come up with your graph looks like, oh, I did a couple of look at them. It's not just empirical. So what you need to do is do a yeah. Okay, so 25 is your distance, by your time, right? We're opening your initial velocity is 0, so this is times by 2. And the acceleration to the fire shape delta D over you don't know what to do, but hey, what are you guys doing? I know what first I have to go deal with the 4-year-olds. Why are you guys being 4-year-olds? Austin, give me the truth. Did you know that I have qualifications to run a daycare, like a little child daycare? It's a long story, but sometimes I use those skills. You gotta deal with the daycare first. I'm coming to you. Oh yeah, I gotta talk to Alex and Will. Okay, so it's gonna be Renee, Blair, Alex, and Will. Yeah, I was fine. That's what you're waiting on? Sorry. God. I know what you did.
What? Why?
I gotta go.
So what you're saying is when you do this, you go to that. You go 825. Very well.
One day. Get it?
No times. Okay, so Will and Alex, come on down. You count with 2 maybe? Yeah? Okay, let's get the baseball squad over here. Squad. Well, I heard it was kind of coming from behind too. Kind of. I mean, you did a group. What are you arguing? You guys realize you want it, right? You're already on the way. Okay. So scientific notation is simply a way of
Big block. Big block.
You guys did it. So like if I've got like 4, 3, 0, 0, I don't want to write it. So we're going to call this 4.3. We're going to move that decimal place. We're going to 10. That's 4.3 times 10 to the 10. You actually do that. So that's how scientific notation works. It also works the other way. 0, 0, 0, 0, 0. 1, 6, that could be 1.6 times 10 to the minus 19, depending on how many times you do it. So what you're really asking me is, how do we do that on a calculator? That's what you're really doing. 709 times 10 to the 12. Right? So you get 7.09. You've got, no, don't go back. That is times 10 to the 12. And then you go 12. Okay, so that's how we got it. There is 7.09 times 10 to the 12. It's always the times 10 is 7, right? And then we're going to divide by 0.3. We'll divide by 0.3. Okay, so your answer is 2.36 times 10 to the 12. Oh, oh, you just divided by 3, so it's 2.3. Yeah. 13. June times again? 7.0. Oh, let's supposed to be minus 12. That's what. I didn't, you know what, you guys? I just realized I made a little tiny boo-boo here. No one caught it. This number here should be negative, right? Negative 12. Maybe you guys didn't even. Right here. I moved it from here to there, and I missed that negative 12. But I didn't make the mistake. I just wrote it down wrong. Like I typed it in right. I wouldn't even notice that on the test if you got that. I'm just looking at it. I made that. Is that enough? Do not go times together. Worst way. Well, this case now here, this is the electric first top. This is actually right? Blair. There you go. Good. Okay. Maybe I didn't come back. Did you figure it out? I don't know how to go back. Well, you know what's all? I'm happy to help. You tell me what I would like to get some reminders tomorrow. And then if I'm not here by 12:30, I'll get this stuff in. Okay. Can we do it at the same time? Reminder, you need a ruler and a protractor as well for the exam. Don't count on me. Yeah, usually force. That E is measuring Pascal. I have a question too.
Obviously, there's a rule because it's out of house.
Yesterday. Today? Are you done with pizza? Or you still
I knew it was something like that.
okay, we need to get those done. To Austin, he needs to not be your son. He needs to do business.
No, we can too.
And I know you take the service from home, because I asked you if you were. Remember that?
It was in my car. Yeah.
It's so you took it home to left in the car. Sounds like a definite. I guess I'm gonna have to break down for the next time and make sure people want to be the whole production. Okay? What about this part? Okay. So yeah, it's done now. Okay? Build the time, go back in time and say it's done. No, what is it? I could, I go back and I tell you on the first day and say smart now.
Are you gonna be here, lunch?